As Matt said, I will take questions. I can't see anybody or any questions right now. And so this presentation is intended to be about 45 minutes with about 10 to 15 minutes for a Q&A at the end. As you can see here, the title of the conversation today is around Standard 241 and how electronic air cleaners came to be underneath this standard. What's very interesting about the way the standard got put together was that ASHRAE was asked by the US COVID response team when they were kind of formalizing everything. They asked them, what do we do in case of the next outbreak, whether it be a pandemic or something localized? Can we take all of our learnings and we put them into one standard whereby engineers can now start to actually design to improved risk mitigation within the air quality, within the air. And air itself, the indoor air quality, is now starting to be considered more around this idea of how do we make a building more resilient. And so that's really the general genesis of this standard. But what is, I think, of interest is not only have they put together something that we can actually design to, they put together some language that we can actually talk to, and I'll introduce new terms. But they've also created now a platform that's very helpful for the electronic air cleaner industry, so that it's a common platform with standards and performance metrics that have to be met. And so as engineers designing into building, we now have a standard that we can point to that says, look, you need to at least meet these safety parameters and these performance parameters for you to pass what ASHRAE is asking for. And so the evolution of 241 is very interesting. We will get into that, but we will also get into how you calculate this and how you actually can analyze the test reports that OEMs are required to hand to you. This is what the agenda looks like. I'll get in, as I said, to a little bit of the purpose and the key terms and the scope of what 241 is intended to address. I'm going to talk also about new terms that you hear known as equivalent clean airflow. We'll talk about how this requirement supplements or fills the gap that the ventilation rate procedure or 621 does not address. We will talk about all the requirements that are required within electronic air cleaners. I'll go into a deep dive on how the test report looks and how to review a test report. Filtration actually does show up in 241, as you would expect. However, there are higher standards that are required for filtration, and so we'll discuss that. And then ASHRAE has done us a favor by putting together a calculator so that we can use that. So I'll show you that. I'll conclude with some kind of commentary at the end. And then along the way, there are opportunities for us to stop and think about it. I might open it up for some questions depending on how this works, but we'll address it as we go. As I go through this presentation, I have this kind of pause slide called the engineer's perspective. And really what I'll do is I'll pose these questions for you guys to be thinking about so that we can address it during the Q&A, or if Matt wants to stop me, we can address it there if there's an important chat comment in the chat feature there. But one of the first aspects to this is we came through the pandemic. Engineers, owners were doing everything we could. The public health information was constantly changing, as we remember from 3-4 years ago now. But what's interesting is as we look back and as we start to actually analyze what 241 has put together, the question we want to ask ourselves is, did we make good decisions? And you can actually now test were the decisions that were being put in there actually of substantive value to the buildings that you were looking to try to help reopen and the occupants that you're looking to try to protect. As I mentioned, we'll get into what's very interesting from the perspective of air cleaners that now are actually being recognized as a way to improve the infection risk mitigation or infection risk reduction within that space. Very interesting and really kind of a watershed moment for the industry. Here are some key terms that I want to introduce, and we'll talk about these at length throughout today's conversation. One of the key terms here is kind of a new mode that ASHRAE is introducing. So as we think about the modes that we designed for today, we have a night setback mode, you might have a warm-up mode, you have obviously your normal mode. You also have a fire mode. We designed for fire in case of a fire, so think about a stairwell Oftentimes the stairwell is typically negatively pressurized, but if you have a fire, you would actually turn on an extra fire-rated fan to pressurize that space so that you can evacuate the smoke out of that stairwell chamber and then allow people to exit. That would be the fire mode, and you have a fire marshal that might come out once a year and test that to make sure that it is in fact still operating correctly. What ASHRAE's done now is they've added an additional mode into the standard, which they're calling the infection risk mitigation mode or infection risk management mode. And what that is intended to do is when the authority that has jurisdiction within your area goes to your local building official or building operator and says, hey, look, there is, let's say, an outbreak in this area. There is maybe it's a school. They can leverage this for the stomach bug or the flu is going around. Some aspect of this whereby you want to increase the rate of response for infection transmission risk and lower your risk mitigation inside that space, you go to the infection risk management mode. That's the intention of that. And as part of that, they've introduced a term that they call the equivalent clean airflow rate. And I'll get into it, but it's really designed for CFM per person. And so they give you this ability now to calculate every type of added feature within that breathable zone, get some sort of calculation so that you can then determine does it meet the summation of what you need for the equivalent clean airflow rate. I'm going to also notate there that you see there's a sub-I, so it's ECAI. The I stands for infection. This is important to know for future standards as they're starting to look at potentially other ECA calculations for gas and potentially for particles. But for our purposes today, when I say ECA, I'm actually discussing ECAI. And notice the components: outdoor air, filtered air as it's recirculated back into space, and then obviously air cleaners that can disinfect that space and the breathable zone. All those things are actually appropriate. I'm going to pause here and actually recommend that if you have not read the foreword that ASHRAE wrote in 241, it's actually really worth a read. It's very interesting. It's about 2 pages or so, but it's a very interesting read. And I'll just read this piece right here just to kind of highlight where this major step forward that they've taken. The requirements for filters and air cleaner testing incorporated in the standard go well beyond what is found in current standards. They are a major step in the direction of creating a uniform and effective technology, agnostic criteria for performance and safety. Ultimately, this should enable more widespread and confident applications of these technologies. And the technologies they're talking about are obviously the electronic air cleaners. There's been a lot of speculation and concern about how do we measure various technologies compared to one another. This now sets a baseline standard. You have to demonstrate performance in triplicate, and you have to demonstrate safety in duplicate. I'll get into each of these reports, but it's a very major, very big standard. The other aspect that they mention here is that it goes well beyond current standards. If you look in 62.1's table, at the bottom of that table, they actually explicitly state that the design of the ventilation rate procedure, it does not include infectious transmission, such as viruses and bacteria in the air. And so they actually make an admission that the current standard isn't intended to mitigate any of the transmission risk, and thereby 241 is intended to fill that gap. And so that's really kind of what they're indicating here in this statement. And so let's get into what is the standard and what are the actual testing requirements. There's a lot on this page, so I'll go through it in a little bit of detail. The first thing to note is that in order for us to meet 241, the design of the building has to first meet one of the prerequisites. So the prerequisites are 62.1 for commercial, 62.2 for residential, and 170 for your healthcare. Those are the minimum ventilation rates, and you can meet them in any of the calculations that are in there. So for instance, there's your natural ventilation calculation, your indoor air quality procedure, and your ventilation rate procedure in 62.1. Any one of those that meet that standard then meets the 241 standard prerequisite. As I mentioned, the air cleaners that are used, you have to have demonstrate, the OEM has to demonstrate that they've done independent third-party testing for the effectiveness in triplicate and the safety in duplicate. And on the right, I'm giving you a screenshot of what the normative Appendix A is that they point to there in that bullet. And notice there's all these different requirements and testing procedures. And again, I'll go into some of these in some detail, but what's very critical as an engineer, and what I ask my engineers to do, is at the very least, look at the safety standard there and add that to your specification when you design for electronic air cleaners. And I'll point out what it's encompassing as far as which products or which technologies, but there is now the safety standard that should be included. So even if your local state doesn't adopt the standard as a code, you at least have it as a standard that you can point to design around the safety standards of the technologies that you're incorporating into your facilities. The standard method for effectiveness, as I mentioned, is ECA. I'm going to show you a table here on the next slide or two to actually help you understand how we design this. And then the comparison between all different types of equipment really helps with the effectiveness of the standard and with your ability to actually now design to two types of, any type of product in there. So let's pause. I know I introduced a handful of different concepts here. This new standard or new concept of equivalent clean airflow, known as ECAI, I think will be very helpful. It's for CFM per person. It is a supplement, so 241 supplements 62.1, 62.2, and 170. It does not replace it. And in fact, 62.1, 62.2, and 170 is the prerequisite for 241. There's now a standard for evaluating the air cleaners and how they deliver clean airflow for the risk mitigation and for safety, for device safety, which is very important. Oftentimes you get asked, what are the products? And I know I alluded to that. These are all the different types of products that actually would qualify under the standard. They could be all sorts of ionization products, like soft ionization and hard ionization products, UV or UVC products, photocatalytic oxidation products, hydrogen peroxide. All of these products must pass the safety limit safety limits that are listed in the code for generating ozone, formaldehyde, and particles. Those are the three safety parameters that ASHRAE has laid out in explicit detail. And so you can ask yourself as you're starting to design, what air cleaners am I recommending? And will they meet these requirements? And so let's kind of dive into that here in a little bit of detail. So equivalent clean airflow, ECA, is actually really a very simple concept. What's I think more interesting is how you actually decide to go about this. So the first thing I want you to look at is the calculation on the left. Very simple, but you notice the volume that you need to design for, the CFM per person, or the total CFM for that room, let's say, is the ECAI number on the category on the right, times the number of people that you're going to have in that space. And so first and foremost, you actually, in your building design standard that you write for the IRMM, could actually include, hey, I'm going to reduce the number of people in this space. And I'll give you a good example. In a waiting area for an office, we all know during the pandemic, I know where I was living, we were often told, hey, don't come in, check in online and we'll call you when you can come in. Well, you might have a room that's set up for 60 people, but they might only want to have 30 people waiting and the other 30 waiting in the car. That could be one aspect to this calculation, is simply source control of how many people you have in that space. Now for schools, you really don't want to have people at home learning. I know many of you had to deal with that with your kids learning at home. And so that might not change. That might be an area where you just simply keep the number of people in that classroom and you work through how does the calculation, what does the calculation require for increasing that risk mitigation, the IRMM. Now look at the right side. So look at this table, and what you'll see is that you have these CFM per person as it relates to ECA, as it relates to these categories. So I'm going to just use classroom for today's example. So go down to that third section, you'll see education facilities, and notice the classroom has an ECA of 40 CFM per person. And this is oftentimes when I do this in person, where I get a lot of people kind of with surprised eyes and surprised looks, because you think, wow, I designed a space for 10 CFM a person for outdoor air, and I now need to design for 40 CFM a person. It's often why when you read the forward, they talk about a layered approach here. They don't expect us to all just design for 100% outdoor air or a wide increase of outdoor air. because it's a very expensive approach, and many of our existing facilities, the building can't handle it. You can't open the ventilation even any more than what you have already. And so for that matter, you can layer in other technologies to get from, let's just use this 10 as the example, 10 CFM a person to the ultimate 40 CFM when you want to get into the IRMM mode. I also want to point to you, if you kind of scroll your eyes up and down these numbers, what you'll notice is that the way ASHRAE has positioned this is that the areas of higher risk are the areas where the numbers are higher. So for instance, the highest risk that they perceive for the risk of an aerosolized infection would be a waiting room in a healthcare facility. And that makes sense, right? People are coming in sick, you're checking them in at the check-in area, and then you're asking them to sit in a waiting area next to all sorts of people who are yet to be seen in the back of that hospital or healthcare clinic. And so that is an area of very high risk, and that is an area that requires 90 CFM a person of ECA approved air. And so the calculation is very simple. What's more interesting is how you go about accomplishing it. And so delivering this clean air as it relates to 62.1, you obviously operate in this current standard for 62.1 or 170 or 62.2. And what you'll notice here is I'm comparing now the prerequisite or the existing code that we have with this new standard, and potentially it might be a code at some point in your area. And so I want to give you just a quick understanding of the additional increases and the additional requirements that ASHRAE has layered into this. The outdoor air, same. You can add the same amount of outdoor air in both. Notice though, we typically have a pre-filter that's sometimes a MERV 8, oftentimes rooftop units are a MERV 8. MERV 8 does not apply in the 241, meaning it does not count under the 241 ECA. What does count is a MERV 11, and as of January of next year, they've actually changed the requirement from a MERV 11 to a MERV 11A. For those of you who don't know what a MERV 11A is, the A is a separate or an additional test that the filter companies would have to provide that actually demonstrates what is the mechanical rating of that filter, meaning you remove the electrostatics on that filter and you just test the mechanical efficiency of that filter. And so they want a mechanical efficient filter of an 11 to meet that standard. That's the minimum rated filter for 241 that would meet ECA. UVC is still approved. However, the UVC OEMs will now have to demonstrate that they meet the safety and effectiveness testing, leveraging the normative Appendix A that I've already laid out. And then obviously all other air cleaners, such as ionizers, would have to also meet that same effectiveness testing in the Appendix A. Looking at this a little bit deeper from a cost perspective, now there's obviously an added cost that we'd have to add to our buildings and to our systems. And so I've laid out here just a handful of different ways in which to think about this for various different VRPs compared to 241s or ECAs. Notice what I've underlined there. So see the classroom age 9+. So a typical classroom on the VRP is about 950. Its average people is 33. The ventilation rate procedure would get you to 444, approximately 13 CFM a person. If you then move to your eyes to the right there, you'll notice if you were to do the ECA, I've already noted it was 40 CFM per person. And so you would have to add an additional 27 CFM per person, or a total add of 876 CFM per person, using just a rough order magnitude of $2.50 a CFM for outdoor air. That's a rough order of cost of $2,190. So it just gives you just a rough ballpark of what that increase might be for that particular classroom. I travel a ton. I'm actually calling in today from Canada, doing some calls up here and some business meetings. So I'm in the airport a lot. Look at the transportation waiting area. I, for one, would always like a lot more air, a lot more cleaned air in these gates that I wait at. And so notice the basis of today's 62.1 only requires about 8 CFM per person when you run the VRP, and you would have to add an additional 52 CFM per person for a cost of $25,950. So you can see there is a cost implication here, And so this is partly a lot of the conversations that I understand are happening both at the DoD level and the GSA level with ASHRAE as to how they might implement this federally. And then our expectation is that these types of conversations are also happening at the state level to some various degrees, depending on your state. Now dive into the calculation. This is not nearly as difficult as it looks, but we are showing you exactly what's in the standard, and I'll kind of unpack this with a little bit of detail. First thing to notice is you calculate up what your total volume of air is, obviously. And so that volume of air has to be equivalent or greater than what the summation of what you're going to add into the system. Traditionally, you don't see a lot of natural ventilation. So if you work your way from the right to the left, you notice that natural ventilation, if you are going to do any, that would actually count as 100%, whatever you bring in naturally. If you aren't doing any natural ventilation, that's obviously going to be 0. The next one is the summation of all your air cleaning systems. That's the ACS there. And if you notice in the picture, they can be, ASHRAE is allowing you to have them in any, in a various different forms. So they can be something that you put in the room, something that you put either in the ceiling or in the plenum above the ceiling, something that's servicing a larger aspect of the space, both in the plenum. And then the MVS would be what's sitting in, let's say, your main mechanical ventilation system or your air handling unit, so long as you calculate the percentage that's actually going to that space, which I think makes a lot of sense for everybody here. And so you add up all these different aspects, whether it be filters in the unit, some sort of air cleaning system in the ceiling, and you make sure that that summation meets your total ECA that you need to meet. We'll go through a calculation here in a little bit, but that's really the breakdown of how the standard is written. And so just kind of as a kind of a pause for this engineer's perspective here, ASHRAE is recognizing that the ventilation rate procedure is designed for dilution of contaminants like CO2 and VOCs. That's really what the 621 states, but it is insufficient for infectious particles in the breathing zone. They actually state that. And they talk about the fact that, kind of the why on this, if you read the forward, is that we do understand more about infectious aerosols as they've worked with various different experts over the course of the years. And in fact, even the World Health Organization as recently as May 1, I believe, they've came out and actually corroborated a lot of the same science that ASHRAE is now speaking towards, which is what we know about infectious aerosols is that if it's happening in the space, it's very, very, very likely that it's staying in the space. And they've mentioned this in various different formats in science and articles. And so if we can manage what's in the space a little bit differently than simply just dilution doesn't treat the infection. It just simply manages to the CO2. Meeting the volume of equivalent clean air will likely require other controls beyond minimum ventilation. That's obvious, and that's really why this layered approach is really, I think, most interesting. What are you going to turn on when you want to go to the IRMM? How do you balance the complexity of what you want to design versus the capabilities and the cost? Those are going to be all part of the conversation that you have with your owners, and the engineers will have to figure out as they design it. Do we understand the trade-offs between what is really considered cleaned air inside versus what is going to be outdoor air that you have to clean? And then is it helpful for us to compare the approaches to deliver adequate volume of equivalent clean air, meaning doing various different scenarios? And that's where the calculator comes in, and it's very interesting. And so kind of now moving into this, what's considered section 7 of the 241 code is or 7.4, excuse me, is the electronic air cleaners. And so you have under 7.4 the ability to add something that could be a lot cheaper than outdoor air, but you do have to make sure that it meets the normative appendix A, as I mentioned, which is effectiveness and safety. And so let me get into that. And I'm showing you pictures of all sorts of versions of air cleaners that ASHRAE has stated could be approved. And they're ultraviolet, electrostatics, photocatalytic, and ionizing air cleaning systems. And so to apply the standard, the first thing I want to walk through is the safety standard, but understand that the safety standard is required to be done in as big a facility as we can find in biosafety level 3 labs. And what's nice about that is that gives you a real world application, because you can take those results now and extrapolate them into your real world scenario that you're trying to design for. And what are the 3 safety parameters? One of them is known as UL2998, and that's measuring the ozone emission from that air cleaner. The second one is ASTM D8407, and that's measuring any formaldehyde generation that's coming from that air cleaner. And then the third one is an ISO classification known as 14644, and that measures any particulate concentration that's being added into the space. And so I'll highlight that when I show you the report, but just recognize that the effectiveness and safety now have to be performed in identical operating conditions, meaning previously there were some potential loopholes where you could find a manufacturer who was designing their products or altering their products to be tested for safety in one test, and then separately for effectiveness in another test. And the simple way to understand that would be, you could take a product that potentially you can turn on high for effectiveness, but then you turn it on low for safety or noise, let's say, right? So those were the pretty some of the loopholes that ASHRAE is trying to close up here in 241. As we mentioned, it has to be a third-party test. The chamber size, the minimum chamber size that the OEM has to go find and use for an independent third-party testing is 800 cubic feet. That's the minimum test. So it's 10 by 10 by 8 if you think about it spatially. You have to operate it in accordance with manufacturer's instructions. You can't alter the product as an OEM and have them operate it differently. It has to meet what is out in the marketplace. As I mentioned, it has to be done in triplicate. And so they do that in triplicate actually both first with the cleaner off, then with the cleaner on, and you apply all of them as the average to the net reduction calculation between those 2 tests. You can't take the best case scenario. There has been instances where some OEMs have advertised their results, but they were only taking the best of the tests that they did. ASHRAE now is requiring that you average all 3 tests out. And then the effectiveness test has to be conducted with MS2. The reason why they choose MS2, there's a handful of different commentary on this. I'll add some at the end. But MS2 is selected because they believe it's safe. It's not tied to any specific pathogen, and in fact, it's not harmful to humans. And so you can go to a biosafety level 1 lab. And so as part of the standard though, air cleaner manufacturers are encouraged to test with specific infection pathogens. So you can get more specific performance claims. So for instance, MS2 is an opened enveloped virus, where most infectious pathogens, in fact, all that we know today, are closed envelope viruses. And so it's not a perfect surrogate, but ASHRAE has chosen this for various reasons. Obviously, safety, as I'm noting here, being one of their main points. This is what the chamber could look like. This is one example of one of the chambers in one of the third-party tests. And what I want to point you to when you look at the test is when you get the results, there's a handful of things you want to understand about the results. One, was it done in triplicate? You can see the 3 lines there. 2, did they do both the off, meaning just test the natural decay, and then test with it on, with the technology on? And notice the key here that's very, very important to understand is the slope net reduction, meaning notice how fast that slope is going away from the natural decay. Because I would argue that the first 10 minutes are more important to you than the first 30 minutes. Why? If I have a child in a classroom and they're spreading virus, the first 10 minutes I want to get it out as fast as possible. I obviously want it to continue to work over time, but that initial blush is very important to get it out very quickly. And so this calculation, what the results will give you is an ECA number that you can then plug into this formula that I laid out earlier. And so you'll get the net slope reduction times the chamber volume, which will give you an ECA number. That ECA number you can then apply for CFM per person into the code, into the standard, excuse me. Okay, so let's kind of review what I just walked through. Standard 241 is raising the bar for air cleaners, and it's actually really helping all OEMs ensure that we're providing more professional and in a more scientific way to comply with repeatable results. It gives the engineering community a lot more confidence around the products that are being designed and around the products that are being offered into the space. I know I, for one, am very happy about that, to help with the category's confidence level as we talk with engineers and building owners. Hey, if you're meeting 241, you met this bar for safety and effectiveness. The effectiveness testing actually closes a lot of these common loopholes that I talked about. It has to be done in that 800 cubic foot. You can't do it in a small, what they call shoebox test. It has to be configured so that the same test is happening versus doing different tests for different passes. The net reduction is what you're actually really is what you're really looking for. And so the question is, like, how do you make that meaningful for the space? Well, now you have the ability to take what you've seen in that 800 cubic foot test and scale it up to the appropriate population size in that real world scenario versus the challenges that potentially were difficult before. Meaning you might wheel something into a room and it's really not designed for the size of that room, and so you end up with an undersized, let's say, concept in a room that really needed something either a lot more or a lot more prevalent than what you'd have. Okay, so the testing report requirements are quite stringent. I will go through this in a little bit of detail, but I'm going to show you the report so you'll see how simple it is to read. First, make sure that the report is done by an independent third party. They have to detail in this report the testing, the results, and they have to ensure repeatability. They have to also describe what the test was, how the test was laid out. So you need to know the chamber, the size, the surfaces, where the equipment was, what was the measurement accuracy of that equipment they used. There's also going to give you a noise. It's not a pass-fail requirement, but you want to know if you're putting something in the space, how noisy is it? And if you're using UVC, they have to measure the electromagnetic radiation level that UVC produces. And then you compare that to the safety threshold levels in 241. Running down this list, as I mentioned, it has to be in triplicate. The net results, it's the average. You can't pick the best. I've already talked about the chamber size. I've talked about the detail equipment. The chamber environment, you have to prove that the environment had a stable temperature and humidity, can't vary greater than 10%. Also, the triplicate results, I have not talked about this, but you can't have wide variations in those triplicate results. They have to be within plus or minus 5% of each run. This is kind of important. You have to run the cleaner in all modes that are provided. So if the mode, if it's, I'm just going to say like a high, let's say high, medium, or low, medium, high, the test has to demonstrate all three modes. And so if you have a product that has various different modes, ensure that when you review it, that all those modes were tested so you understand how that impacts, whether it be noise, safety, as well as effectiveness. And then you take the net reduction slope. That's what you calculate into it. You could see there on the right, there's a lot of things there to look at. But if you just go to test 2, you'll notice there the K sub TD compared to K sub ND. That's your net reduction, and then you get that net reduction and you multiply it by your volume, and then that gives you the final result. So in this example that I'm showing you here, that final result would give you an ECA for that product of 212.96 cubic feet, CFM, per minute. And then when you look at the report, these are the 3 safety testing that I talked about, and this is what the report would look like. And so formaldehyde is something that can generate both off-gassing as well as be created through through a limonene test, and that's actually the test they require. So in this particular test, what you do is you evaporate limonene, which is kind of a benign VOC. It's in all your cleaning products that have lemon or lime scents, and so they use that for safety, obviously. But in the presence of an electronic air cleaner that is fracturing or creating indoor air chemistry, it would actually fragment that limonene and create formaldehyde. And so they have to prove that in this test, that you do not produce greater than 50 micrograms per hour of formaldehyde, and you would get a pass-fail there. You can see there, green would be pass, red would be fail. Notice the ozone test, the UL2998. That parameter is less than 5 parts per billion. It's actually known as the zero ozone emissions test. And the reason why it's nominal 5 or nominal 0 rather, is that the testing measurement devices have an error reading on it of 5 parts per billion. And so that's nominal 5. So as long as you can be under that, you would have a pass. And then the particulate is the ISO standard that I mentioned. And what's interesting there is they set the chamber up to a class. The class has to be no higher than a class ISO 5. And then the device, when run, cannot exceed 1 level above that class. So for this example, you can't exceed, if you set the class up for 5, you can't exceed class 6 in order for you to pass. And that's the particulate count. And so that's how you can actually understand reading these from the safety test. And I think you can agree with me, it's actually really stringent. It should give you a lot of confidence when you see these reports and then you go to recommend or design around a particular electronic air cleaner, that you're adding a really good effective solution that is extremely safe. And so that's really kind of part of this perspective. I jumped ahead on this, but hopefully what you'll see there is that both the effectiveness and the safety test gives you good confidence in by understanding how to read the test report. And as I would recommend, I would ask that you add this into your, I would suggest that you add this into your specifications if you are going to include electronic air cleaners. It's really kind of a watershed moment for the category, and I think it's a big step forward that ASHRAE has done as a favor to the entire industry to help provide boundaries for what is an appropriate solution to provide better air quality within these spaces that we're designing. Filters are included, as I mentioned, and so just to give you a little bit of highlight of what I meant, so you don't have to do any safety testing for filters. It is a 52.2 single pass test that they have to demonstrate, but they, as I mentioned, they only require MERV 11, and actually it will be MERV 11A as of next January. And so that is your minimum requirement to actually get an ECA value. You can run any sorts of filters in there, but in order for it to count towards what you're circulating back into the space, you need to have a MERV 11A filter for next year. And you get certain percentages. So let's say you're bringing in 500 CFM of air, you would take a percentage of that based on that filter, and that percentage gives you an ECA number. And in truth, when you look at this percentage, it's on this slide here that I just showed you, you actually get a lot of value. They give you a lot of credit for filters. And so let's say you had a space that was just cleaning with a MERV 11, and as I mentioned, you were doing 500 CFM. So 60% of that would be what, about 300 CFM? And if you had, let's just say you had your 30 kids in there, you could see you're getting a significant amount of CFM per person of equivalent clean airflow inside that space. And so you add that to the outdoor air, and that might get you, just that might get you to the full ECA. Oftentimes what I've seen is it gets you relatively close with a MERV 11, and then you want to add something else like an electronic air cleaner to cover that gap. And the reason why ASHRAE is doing this is they really do understand now that what's happening in the space, a layered approach with good outdoor air, good filtration, and something else that's safe and effective will completely provide a way better scenario for cleaning that space and providing a safe air cleaning. So looking at the engineer's perspective here, you can see that the filters do provide a substantial contribution to aerosolized pathogen reduction. As long as you have good airflow through that air filter, that's gonna work for you in a lot of the cases as a big bulk of the calculation. And I'm gonna show the calculation here next so you'll understand that what it means kind of mathematically. Does the system have adequate return airflow? That's actually a key aspect to this. So as you know, as you go around surveying buildings, you're often looking, what is my air change per hour? Am I getting good airflow here? All those things are required for you to get good, are required within the standard to understand that you're going to get good clean air within that space. Do the systems have adequate capacity for static pressure? Obviously, that's something we've all dealt with. I did an event about a year ago where I was speaking to testing and balancing contractors, and I asked how many people were asked to increase their units from whatever pre-filter to a MERV 13, and almost every hand went up. I said, how many of them had problems with the MERV 13 they added to their rooftop units? And all the hands stayed up. And so we understand that adding these additional filters can stress the fan and could potentially create problems. And so that's where the building owner and the engineer have to get involved and decide, do you add something new as it relates to a piece of equipment? And when you do you add the capability for you to swap in an upgraded filter when you want to go to your IRMM such that you can manage that additional static pressure? The other challenge here, and this is just a little bit of a side, I've seen this and I've heard of this in various scenarios. You designed a one type of filter and the owner sees the cost of that filter. It's a dense, heavy filter for a reason, and they decide to downgrade to another filter because of cost reasons, and so therefore typically not getting to the filter that might be designed. That could be a scenario that you have to work through in your design, in your conversations. So this is a calculator. It is small. I will blow it up here on the next slide to try to give you a better understanding. But let me just help you orient how the ASHRAE has laid out this calculator. So you'll notice there's kind of a basis of design there in the first column, and then you can run various options along the rest of the columns to try to understand what it is you're going to design. And as I mentioned, the calculation is easy. What's more interesting is how you go about accomplishing that new ECA number that you're trying to capture. So what you do is you enter the category, what's that space type? You enter, it then populates what the CFM per person is. You then start to enter what your area, your ceiling height, so you get your volume. You can design for how many people are going to be actually in that room. It will populate what's in the VRP. So if you do nothing, it will populate the VRP parameters. And then you get what your supply area is, what your outdoor area is, and so on. And so that then begins to start to calculate your IRMM just with outdoor air. And then going down into the next section, you start to look at what quality filters you have, what is the UVC, what are you using UV in any of these spaces, and then the next section are any additional equivalent air cleaners that you're going to provide. And then that gives you the basis of design for what it is you're going to design. And then to the right, you can then start to play with various strategies as to trying to meet this. And so let me just blow up this a little bit bigger on this slide so you can kind of digest that particular column, and I'll speak to the example we started with, which was the classroom. So if you look at the basis of the classroom, in this example, we're using what's in the VRP, which is a 950 square foot classroom. General supply air is about 1500 CFM. If you run the VRP with the occupancy of P sub Z of 33 people, and it had a filter of pre-filter of an 8, MERV 8. You could see here that the MERV 8 gets no benefit. The total, your basic design based on just basic 621, you would come up to 13.4 CFM per person, right? So you don't meet the IRMM. Next, let's change out that filter from a MERV 8 to a MERV 11. So now you get the 60% efficiency removal rate. And notice it's a big jump. You go from 13.4 to 32.4. Okay, so now let's go to a MERV 13. And now you go from 32.4 to 37.8. You're getting awfully close to 40. And so now if you add an electronic air cleaner that meets all those safety and effectiveness requirements that we talked about, you now can actually meet, and you go back to a MERV 11. So you save on the filter cost, but you add the air cleaner, you actually now can meet the 241. And so you can see how this can get structured as you want to start thinking about what are the right economic adds to this particular design that you're working on versus how it actually applies to the ECA. And this can work without it being code. I have had a lot of conversations in the New England area with those that are in spaces that do have people with highly immunocompromised conditions. So think about your classrooms, your daycare centers, your healthcare clinics, your dental clinics, even your hospitals. Those are all areas that might just decide, hey, look, this is a good standard for us to apply today because it actually applies really good principles to making that breathable zone a lot safer to breathe. And so let's take an example in a healthcare area. So this is a waiting area. What's interesting about the waiting area, if you look at the VRP, they actually allow for 60 people, which is a lot of people in a I think it's 400 square feet. So if you start laying that out, you're like, wow, that's really tight. So that's this existing code right now, which is quite interesting, right? 62.1 allows for 60 people sitting in a waiting area that are sick, potentially sick, in a 400 square foot area. So we've actually designed this basis of design for 30, and using a MERV 13 filter. So you're already getting an ECA credit of about 77% efficiency against that return air. So that's your basis of design. Notice you need to get to 90 CFM per person, as I notated in the beginning of this conversation. The basis of design gets you to 52.7, so it's quite good, but it's not near what we need to get to. So let's just take HEPA. Let's just go all the way to the top of the HEPA of the spectrum for filters that you can offer. Very expensive filter, very high pressure drop, but should give you really good results. You get, according to this, you get 99% efficiency for all air going through it. And so that gets you an IRMM of 66.1. So again, better, but still not there. So let's go back to that MERV 13, but this time let's add electronic air cleaners that are equivalent in the space that gets you an additional 1,200 of ECA, of equivalent clean air, much cheaper than the filters, the HEPA filter, and now you exceed the 92.7. Sorry, now you exceed the 90 and you get 92.7. So again, you can see how you can apply these and why air cleaners have become very important as something in this space. Is you can run as MERV 13, and you can have these electronic air cleaners that you turn on when you want to provide an additional risk mitigation for potential outbreaks. So a great example of this would be, I have a school and I know the stomach bug is going around. Well, if I can turn on my electronic air cleaners during that stomach bug, or the flu is going around during the winter, those are ways in which you can provide added protection within the space without adding a lot of cost to the general mechanical architecture of the design of that building. And so we come to the last perspective here. And this is a little bit of commentary, but I'm going to apply it here, and I'll be happy to answer questions as best I can. What's interesting to me is that the standard, I think, is very effective. I love the fact that it's standardized, but they picked MS2, and MS2 is, as I mentioned, not something that is effective. It's not something that infects humans, and they've done it for the obvious reasons. But it's kind of a poor surrogate when you think about it from the perspective of real viruses, such as aerosolized pathogens. As I've mentioned, you have influenza. Obviously, we know about coronavirus, but those are better ways to analyze, let's say, an electronic air cleaner. And so they discounted the real value of electronic air cleaner can offer, because an MS2 does not actually operate in the same manner that these viruses would do with electronic air cleaners. And so that might be something that they address later on, but at this point, you don't get the credit that you would get by using MS2. But now, if you then kind of skip into the filter side, they are using a particle that's 3 times the size of MS2. So you get more effectiveness on the filter than you actually would really get if you actually were doing real viruses. And so the filter actually gets more credit than what would really be seen when you start to think about what it is you're trying to design around, which is these ultrafine particles, albeit that being viruses and the others that are transmittable through aerosolized inhalation. And so that's a little bit of the commentary on this, but in general, what is interesting is you do get something that's a standard for all, that actually applies, that can then start to provide a background for everybody to start to kind of step from. And then as engineers understand this disconnect between MS2 and real viruses, and how filter efficiencies really work with these ultrafine particles that are not being tested on the filter, you can actually start to then tweak your designs to even better systems and healthier, cleaner air than what the standard already is leveling us up to. Last thing here on the conclusion is, taking my commentary aside there, the standard does demystify and standardize a critical set of conditions for tools for the indoor air quality. ASHRAE 241's control of infectious aerosols is a watershed moment for us as an industry and is a major step forward in addressing indoor air quality and infectious aerosols transmission. We recognize it's not currently code right now, but part of what we're doing today is just educating the engineers and the building owners within our community to try to allow everybody to kind of understand how you potentially can start applying this, whether it be just applying the standard as part of your spec, or actually leveraging the total design feature of this within your standards where appropriate. Do recognize that ASHRAE has pushed this out very quickly at the request of the COVID response team, and so they did this. I think it was roughly in the order of 6 months. It got released last June of 2023, and so they have mentioned that it is under continuous maintenance, and so we should see more changes coming. But the basic skeleton and the basic calculations, everybody stacked hands and they agree. These are really good principles that we want to start to apply to our buildings. And finally, as it relates to air cleaners, you know, what is great, and as I mentioned at the beginning, this is an important engineering control that we can leverage, and it should provide you a lot more confidence and widespread adoption as you start to introduce these to your buildings and to your customers alike. And so with that, thank you for your time.